Hey, welcome everybody. We're in lesson 4, talking about differentiability and continuity today. Really important topic. So in this lesson, we're going to investigate that relationship between differentiability and continuity, and when a function fails to have a derivative. A function that's differentiable at a point is called locally linear at that point. Basically, it's telling us in order for a function to be differentiable at a point, the graph has to be continuous and smooth at the point. Remember, when we say that a function is differentiable, we're saying that the derivative exists there, and we're able to take a derivative. So let's jump in here. The definition of differentiability at a point is the limit definition. We say if a function is f of x is differentiable at some point c, that's going to happen if and only if the limit from the left and the limit from the right are approaching the same real number, finite value, capital L. So left limits and right limits have to be the same. You know, in our last lesson, when we had the absolute value graph and we were talking about the derivative or the slopes, and we wanted to evaluate the slope down there at the corner, this is that case. If you recall, the slope on the left was -2 and the slope on the right was +2. So those left limits and right limits were different from each other. And that's why we didn't have a derivative at that place. And I believe that's going to be our first example. So here we're going to show how the derivative may fail to exist. If you sketch the slope of the derivative of the function y equals x minus 1, the slope graph, this slope is -1, and this slope is +1. So that slope graph at 1, the slope graph, the slope is -1 everywhere negative, and the slope is +1 everywhere to the right. So what's the derivative as x approaches 1 from the left? The slope would be -1. And as x approaches 1 from the right, the slope would be +1. Is the function continuous at 1? Yes. Is it differentiable at 1? No. And the reason we know that, let's write this down because this is like justification steps on a free response question. We would say since the limit as x approaches 1 from the left on the function isn't the same as the limit as x approaches 1 from the right on the derivative, there is no derivative. No derivative. So they're not the same. Whoop. Take a look at the graph of the cube root of x, and using the alternative form of the derivative, can you show that the function has a vertical tangent line at 0? Well, the alternative form would be the limit as x approaches 0 of the cube root of x minus the f of 0, which is going to be 0, divided by x minus 0. Remember that definition from earlier. Simplifying this, we're going to get the limit as x approaches 0 of the cube root. I'm going to write the cube root this way, x to the 1/3 divided by x to the 1st. Simplifying that down, that's going to be the limit as x approaches 0 of 1 over x to the 2/3 power. which is 1 over 0. No division by 0. That's how I know limit's undefined, because I've got a vertical tangent line. This is undefined. No limit. Can't do that. In this example, if we're given the graph of f of x is 1 over the quantity x plus 2 squared, describe the derivative of f as x approaches 0 from the left and from the right. So we could just do that real simply here. I could say as x goes, as x approaches negative 2 from the left, the function, or the derivative, is approaching positive infinity. So as I go from negative 2 from the left, my slopes are getting infinitely large. And as x approaches negative 2 from the right, the derivatives what are they doing? These are getting positive slopes. These are getting negative slopes, but more negative. Therefore, we can say f is not differentiable at negative 2. In part B, given the derivative is this expression, use the formula to evaluate the derivative at negative 2. Whoop, my pen disappeared. So back here, f is not differentiable at x equals negative 2. So we can evaluate that by using both definitions. So f prime at negative 2 from the left, we could consider that we're evaluating here in this small neighborhood. I'll say negative 2.1. And you got to think about the behavior and the size of numbers. So I've got negative 2 over negative 0.1 cubed. So if you think about the value of the numbers, I've got a negative divided by a negative, and a little small number in the denominator is going to create a positive large number. And f prime at negative 2 from the right, using this expression again, what's the behavior of the function on the right side? 2.1. Nope, on the right side, not 2.1. We're heading to negative 2. So on the right side, we could say negative 1 9/10. How about that? Close little neighborhood. So again, thinking about the behavior of the numbers, I've got a negative and a negative, a positive here. So a negative on top and a positive on the bottom. A large number divided by a really small number, the graph is going to be unbounded, or the derivative is going to be unbounded. So we looked at it graphically up here, algebraically and numerically down here, based on the definition we saw about differentiability at the point. The left limit and the right limit, they're not heading to the same. So the derivative at negative 2 does not exist. I'm using abbreviations here. Then differentiability implies continuity. Super, super important. If a function is differentiable at a point, then it's continuous. If a function is differentiable at a point, it's continuous. Important. So differentiability means it's continuous. It doesn't mean continuity. It means it's differentiability. Doesn't work the other way. A sharp corner, a cusp or a vertical tangent line are the places where you cannot take a derivative. It's continuous, but it's not differentiable. So if a function, differentiability implies continuity, but continuity doesn't imply differentiability. We've seen that with these examples here. Write the contrapositive to the statement. If a function is differentiable at x equals c, then the function is continuous at c. Who thought you'd have to write contrapositive statements in calculus? Can you do it? If f of x is not continuous, at x equals c, then f of x is not differentiable. At x equals c. Example 4, describe the x values at which the function is differentiable and justify your answer. So here, let's look at our problem areas. That would be where the argument is 0, which would occur at positive or negative square root of 5. So the x values where it's differentiable would be from negative infinity up to negative radical 5. Then in between from negative radical 5 to positive radical 5. And finally at radical 5 to infinity. So here I've got a continuous function, but I don't have differentiability at square root of 5 positive and square root of 5 negative. There's a cusp or a corner there that causes no derivative to exist because the g of x has a sharp corner or you might want to call it a cusp at the points, negative square root of 5 and when x is positive square root of 5. So there's my justification for that. In the next example, example 5, can you find the values of x where the function is differentiable? So you can tell where our problem areas are looking at the subdomains here. At 0, we've got x plus 1 squared has to be equal to 2x plus 1. So I've got to check to see if, first of all, if they're continuous. So you've got, when x is 1, you've got 2 squared. At x equals 0, you got 1 squared, and 2 times 0 plus 1 is 1, so they're matching up there. But at 3, what's happening here? At x equals 3, we need to have 2x plus 1 equal to the quantity 4 minus x squared. And checking at 3, you've got 3 times 2, that's 6 plus 1 is 7. And 4 minus 3 is 1. 1 squared is 1. Well, 7's not equal to 1. And here they are equal, so what can we say? H of x is differentiable at negative infinity to positive 3 and at positive 3 to infinity. But we've got a discontinuity, don't we? There is a discontinuity. At x equals 3. So h of x is not differentiable there. And if you drew the graph, it would be easy to see because your function would be right here. You'd have a parabola going off. At 0, you got 2x plus 1. But when you got to 3, your value was at 7 up here. We found 3, 7 up here. But on the other part, the 4 minus x squared, what was it, 1? At 4, the value was 1. And it went off that way. So you've got some jump discontinuity. You can tell graphically what's going on. But we could also tell algebraically by just evaluating. These two values went to the same y. These went to different y's. Okay, piecewise functions, they're always pretty challenging. So we want them to be connected and smooth in order for the function to be differentiable at a point. So this is what's tricky. I want to find the value of the constant a where the function would be continuous over all the real numbers. So we could do that. You know, here's our target number. Here's our issue. When x is 3, what happens? When x is 3, we can put a 3 in here. That's 9a minus 3 on the left. And what happens when we put a 3 here? We got 2 times a, because there's no x there. So 6a, 7a. 7a has to be equal to 3. So a would have to be equal to 3/7. All that means is that we've made them connected, but what about the smooth and continuous part? So in order to find that out, to justify that, we have to check the left limit and the right limit. So let's justify that. We know that they're connected, but we want to check this. What's the limit as we approach 3 from the left on the function? And is it the same as the limit as we approach 3 from the right on the function? So a is 3/7 x squared minus x, and that's got to be equal to, what was a? 2a. Has to be equal to 6/7. So if we substitute a 3 in here, we got 3/7 times 3 squared minus 3. Is that equal to 6/7? And I'm going to put a little question mark up here because that's what we're checking. So 9 times 3, that's 27 over 7. 27 over 7. And minus 3, that would be 21 over 7. Does that equal to 6/7? Ah, it is. So what does that tell me? The limit from the left is 6/7, and the limit from the right is 6/7. It's true, so then we can say that the function has a derivative. It's continuous over all reals. It's smooth. It's connected, and we've justified that it's continuous. In this one, we want to show algebraically using the alternate form of derivative, yg of x is not differentiable. So if you think about this graphically, we have x squared for x less than or equal to 1. So we have that. Let's try that again. Sometimes I'm challenged with my tablet here. Well, I still can't hit it. And then y equals x from there. So if you just drew it, it kind of looks okay. But I want to think about my target value is 1 from the subdomain. I have a problem. We want to look at that problem. And then I want to think about what's the limit as we approach 1 from the right on that graph, using that alternate definition. As I approach 1 from the right, I'm on this branch over here. I draw my little Randy the Roach guy. Okay, so as I approach 1 from the right, that's the problem area, and the function is y equals x over here. So x minus 1 over x minus 1. That's the f of x minus the f of 1 over x minus 1. Well, that's approaching 1. And then we want to check the limit from the left. So the limit as x approaches 1 from the left is the other piece. Well, if this is Randy the Roach, this is his girlfriend, Rita the Roach. Hey, you got to have some fun. And we got x squared for that function, right? So I've got to do x plus h, or x, f of x plus 1, f of x plus 1. Times x minus 1 over x minus 1. X squared minus 1. Am I doing that right? Let me look at it again. X squared minus 1. I should write that step so you don't get confused what I'm doing. My function's x squared. So I've got f of x minus the f of 1. Then I factored that. I was getting ahead of myself. So this factors to be plus 1 minus 1, the difference of squares, and you can take out the bottom factor, move common factors. And then if we substitute our value in here, that limit is 2. So I have one limit going to 1 and one limit going to 2. Now remember what we're finding. We're finding the derivative, that's the slope of the tangent line. So this slope, we already know this slope has a slope of 1 all along that curve. But this slope, the slopes are changing. And as we come up to the point 1, that slope is 2. So at that point, graphically, lost my graph. Graphically, there's a cusp there or a corner. And we could say in words, here I'm going to erase a little bit of this so I can have a place to write. So you got it? Verbally, we can write this out and say something along the lines of, so this would be thinking process number 4. Graphically, I've got a cusp there. There is a cusp at x equals 1. It's ever so slight. And the justification is this. When we checked the limit using the derivative, alternate derivative definition, the slope as we headed to 1 from the right was 1, but the slope of the derivative as we headed to 1 from the left was 2. They weren't the same. This one was 1 and this one was 2. The derivatives were different. It's continuous, it's not smooth. That's a ever so slightly cusp. I've got a slope coming up like this, and then this going off like that. That's more of what's happening. This derivative is 1. This derivative right here is 2. They're not the same. Not differentiable at x equals 1. Okay, a different topic. Can you estimate derivatives of a function at a point? So I'm using my TI-84 in this case. On the AP exam, you need to find numeric derivatives. It's one of the 4 things you're supposed to be able to do with a calculator. This is the process or the steps if you wanted to use your calculator. On the Inspire, it's a little bit different. I use the scratch pad, and this is the process or the steps. It's a little bit prettier on the Inspire if you're lucky enough to have those. So we could do that. If you use your calculator to find the derivative, you want to be able to substitute into the calculator, find the derivative of the function f of x at x equals -3. And my calculator gave me -11. So at -3, we're going to find out later on that the derivative, if you just calculated just the plain derivative, it would tell you 2x minus 5 using your calculator, and that derivative is -11. So it just depends on which calculator you have and how you use that. So I guess I should have pulled my calculator up in this lesson. Sorry about that. Use your calculator to find the derivative of the first 3 functions in this lesson set and explain any kind of problems that you encountered. So, you know, I love pictures. I know that x minus 1 absolute value looks like this. I know the cube root of x looks like this. And we've already seen 1 over x plus 2 quantity squared. Looks like this. And there is a break in the graph at -2. Okay, so on my Inspire, I'll do the Inspire first and the TI-84 next. So on my Inspire, the f prime at 1 shows me plus and minus 1. But on the TI-84, the f prime of 1 shows me 0. So we got a problem. It's not differentiable. We know it's not differentiable. You can't trust the calculator. On this one, the f prime of 0 on the Inspire shows me undefined. On the TI-84, the f prime of 0 shows me 100. You see the difference between the two? The Inspire has a little more sophistication than the TI-84. So depending on which calculator you're using, you don't want to just trust the calculator. You have to be able to evaluate and use the rule of 4, process through what does the parent graph look like, what's the behavior at this problem area. In this case it was 1, in this case it's 0. And same thing here on the Inspire. The Inspire is going to tell me at -2 it's undefined. But on the TI-84, the f prime at -2 is 0. Now where it got that, that's in a programming issue. So lastly, we want to be able to defend our answers. If you're given that y equals f of x is differentiable at 3, explain why each statement below is true. So this is kind of some verbal descriptions here. The f of 3 exists, tells me if a function is differentiable at 3. So they've given us the fact that it's a differentiable function. at 3. If f is differentiable at 3, then f is continuous at 3. So f is differentiable implies that f is continuous. And if f is continuous, then the f of 3 must exist. Now, I would have said it in a lot more writing than this, but you get the idea. The limit as x approaches 3 of f of x exists. So remember they told us f is differentiable at 3. That means f is continuous at 3. So we could say if f is differentiable at 3, then f is continuous at 3. And if f is continuous at 3, then the limit at 3 on the function would exist. And that's why it's true. Here, what do you notice about this? The limit as x approaches 3 of f of x minus 3, f of x minus f of 3 over x minus 3. Where have you seen that? That's my alternate definition of the derivative, right? Which is telling me that the derivative of the function at 3 exists. That's what this is telling me. If f is differentiable at 3, like they told us, then the derivative exists at 3. This is the alternate definition of the derivative. And that's why that's true. How about this one? This is the limit definition of the derivative, and it says that the derivative of f at 3 has to exist. If f is differentiable at 3, then the derivative at 3 exists. Right? This is the limit definition of the derivative. It's telling me that f prime of x is the slope of the tangent line, which is the limit as h approaches 0 of the f of x plus h minus the f of x all over h. So that was a quick lesson. I'll be here next time with all the basic derivative rules. Have a great day.